It's time to explore our first accumulation function. In this problem, we have 4 students painting a house in shifts. Their hours are given here, and question 1 asks, how many hours does each person work? Well, Chris works from 9 to noon, so Chris works 3 hours. Tony works noon to 4, Tony works 4 hours. Similarly, Sam works 4 hours, and Joe works 3 hours. If, as they go along the day, they put a token in for each hour they work, how many tokens are there at 5 p.m.? It's the sum of the total number of hours worked. So there will be a total of 14 hours worked, or 14 tokens, and again, it represents the total number of hours worked. S of t is the number of people working at time t. So we were asked to graph this. We can start by looking at each hour and see what the graph will look like. So let's label our axes from 9 a.m. to 5 p.m. and each vertical hash mark represents one worker. At 9 o'clock we just have Chris, so there's one person working. At 10, Sam comes on to join Chris, so there are 2 people working. Sam and Chris continue until we reach noon, and here's an interesting part. Chris goes off work, but Tony comes on work. So really, we could imagine that happening at exactly the same moment, so there will really only be 2 people working at noon. We can continue throughout the day, which I'm sure you did. There are 2 people at 1, 2, 3, and 4, and at 4:01, Tony goes off work, and the only person remaining is Joe. What does the area under this graph represent? Well, notice if you add up all the squares, there are a total of 14. That's the same as the total number of hours worked. So yes, in fact, the area under this graph represents the total number of hours worked. So now what we want to do is accumulate work from the beginning of the day. So we will start with our graph of staff hours, and now we want to create hours worked, or amount of time worked, W of t. So it will be the amount of work that has been accumulated starting at 9 a.m. Again, we want to label our graph. At 9 o'clock, no one has worked yet. We just have one person coming on. By 10 o'clock, one person has worked an hour. An hour later, at 11 o'clock, we will have had 2 people working for an hour, so they will have added 2 more hours to create a total of 3 hours worked by 11. And if you continue this trend, what you will see is you have 2 people added, 2 hours added for each hour up until 4 o'clock, where one person goes off work and there's only one person remaining painting the house for the last hour, for a total of 14 hours worked. Then it asks us what the relationship between the graph in part 3 is to the graph in part 4, and you will see here that the piecewise function in 4, which is the work accumulated, has slopes that match up with the output of the staff hours, of the staff working. So here from 9 to 10, we have a slope of 1 because one person is working. From 10 to 4, we have a slope of 2 because 2 people are working. And from 4 to 5, when one person is working, we again have a slope of 1. So what's the relationship? It means that the derivative of the work graph is going to be the staff graph. Or, said another way, the antiderivative of the staff graph is going to be the work graph. And this really is what's at the heart of the second fundamental theorem of calculus, this relationship here. So now let's look at another accumulation function. And in this case, f of x is a crud. So now let's look at a second accumulation function. And in this case, I have some arbitrary function f that's continuous on our graph. And I'm going to define a function, the accumulation function, g of x. So x is my variable. So it's the accumulation starting at an input of 1 and going to x of the area under the curve from 1 to x for the function f of t dt. So for this function here, this is going to be f of t. And I want to ask, what are the different values of g that we get for different inputs? So let's do the first one together. So the first one is g of 3. So that really is asking what's the area under the curve f of t between 1 and 3. So here we have it sketched in. It's the area between 1 and 3 under the curve. And if you count squares, there are about 19 of them, but each one of those squares is worth a quarter of a square unit. So they're 19/4, or say 4.75. Right, let's just see what those units are again. One tiny square here is 1/4 of a square unit. Okay? So can you try to find for me what what g of 5, g of 1, and g of 0 are? Pause the tape here, test your answers, and then we'll compare. Did you get g of 5 was about 6, give or take? Remember that the area under the curve is going to be considered negative. G of 1 is 0 because we're accumulating the area from 1 to 1. Well, that's a line here with no width, so there's going to be no area involved. And then finally, when we look at g of 0, we're starting here at 1 and traveling backwards towards 0 to accumulate the area. Because we're going backwards, the answer is going to be negative. And I hope this doesn't bother you, because when you think about it, when our height is above the x-axis, we consider the area negative. When our height is below the x-axis, we consider it, I said that backwards. When our height is above the x-axis, we consider it positive. When our height is below the x-axis, we consider it negative. There's no reason to think as we travel along the x-axis it would be any different. So as we travel from left to right, the area we accumulate is going to be positive, but when we travel from right to left, the area we accumulate is going to be negative, hence the negative sign here. You're now ready for the statement of the fundamental theorem of calculus 2. I guess our book calls it the second fundamental theorem of calculus. And the idea here is if you're looking at a continuous function on a closed interval a,b, and you create the accumulation function starting at a and going to x of f of t dt, what this says is that the accumulation function that you create is continuous and it is differentiable, meaning it has a derivative. And furthermore, its derivative, the derivative of the accumulation function, ends up being the integrand evaluated at x. So g prime of x, the derivative of the accumulation function ends up being the integrand at x. Before we consider the proof, let's try an example. So you could already see one answer here. What does it say? It says if I want to find the derivative, I'm supposed to use the example from our last picture. So it says g prime of 3. So that's the accumulation function from 1 to x of f of t dt, which is given by the picture we looked at previously. According to the fundamental theorem, this is going to be the derivative is going to be the integrand f of t evaluated at 3. So let's look back at our function. We find x equals 3. We look at the output value of the function here. That ends up being 2.5. So that tells us for our derivative of g at 3, the answer better be 2.5. There it is. Now, each one of these other problems is just a different way of asking for the derivative of the accumulation function evaluated at a particular point. Here, we're taking the derivative of the accumulation function and evaluating it at 5. The derivative is going to be f of 5. Looking back at the graph, you should see that this is 0. Now, you might think to yourself, when's the derivative 0? What does that mean? Well, what it means is that x equals 5 is one of those critical numbers for the accumulation function g of x. This reminds me of the homework problem you had, 5.1.50, where you were given information about the derivative and asked about the function that it came from. So knowing that the derivative here is 0 tells you something about its antiderivative, namely where the critical number of the antiderivative is. This is an interesting notation going on here. Essentially, if you pay attention, it's the integral from 1 to x of f of t dt. That's just g of x. So this is asking for the derivative of g of x evaluated at 0. Well, we know that's f of x evaluated at 0, which is f of 0. Look back on the graph, and you find the answer is 0. So again, this accumulation function that we're looking at, the integral from a to x of f of t dt, is one antiderivative for the function little f of x.